Good morning, everyone. I hope you enjoyed this class. Today is the last day of class. The next thing today is the exam review. The next thing is exam review. We will need at least one student to come. If no student come, I will leave too. Okay. At least one student come, we will take the video and we record it. That student has to come within the first 5 minutes. Okay. Previously we talked about heat transfer. Heat transfer will be in the exam. Okay, and today we have quiz at the end. Okay, we have quiz at the end about flow assurance. This is quiz 6. This quiz is to encourage you to come to class and stay in the class. If you don't write your name, you get 0. If you do everything wrong, you get 5. It is a multiple choice, 4 choices. If you didn't get anything correct at all, you will get just 5. Okay? If you get 1 to 3, you will get 8. If you get 4, you get 9. It is very unlikely that you get 0. It's very unlikely. There are 5 questions, 4 choice each. Even if you do a random guess, you should get 1 correct. But if you don't get 1 correct, so be it. Okay? On the heat transfer, we talk about the formula for the temperature profile calculation. This formula is for the case of constant fluid property. This means U value has to be constant. Okay, for U value to be constant, this means viscosity has to be constant. Every location has to have the same heat loss. Heat loss can happen by air blow across the pipe or water blow in the subsequent line. Water flow across the pipe will cause heat loss. Even if the pipe is buried, heat will be removed by the wind or the water in the subsea, and heat from the soil will remove, and heat from the pipe go to the soil, heat from the soil go to the environment. So even if we have the pipe that is buried, we still have the heat loss. So this equation is for constant fluid property case. Okay? Constant fluid property case. For constant fluid property case to happen, temperature has to be constant, pressure has to be constant, no phase change. That is not normally happen. Okay, so when we do it for the real case, we will have to do discretization. Okay, in the exam, in the homework, we don't do that. Okay, last year I give the module to do that calculation. We decided to shift it to grad level. It's a little bit complicated. The U value is depend on heat transfer inside. Okay, heat transfer through the pipe and heat transfer outside. So when we have the pipe, inside we have oil flowing. Okay, outside we have air flowing or air blowing across the pipe. So heat from oil will have to go through the inner wall through convective heat transfer. That is why we have convective heat transfer coefficient, HI. Heat from the inner pipe will go to the outer pipe wall through conduction. So we have K sub P or pipe thermal conductivity to account for that conduction. And then heat from the outer pipe of the wall will go to the environment through convective heat transfer. Air will carry heat out from the outer pipe. That is convection. So we have H sub O outside convective heat transfer coefficient. Okay, this is when the pipe is not insulated. We have just one layer of the pipe. That's why we have just 1 kP. The unit is in SI, all in SI. Potential question for the exam is asking you the unit of overall heat transfer coefficient in the SI unit is that or not? Is this or not? Is it this? True or false or something? So the unit you have to know. In addition to that, you need to know the equivalent unit in field unit. Okay? The equivalent to what in the field unit is BTU per hour, or maybe BTU per second, okay? The equivalent unit for meter in the field is feet. For Kelvin is Röntgen, okay? Notice that if I change that K to C, everything is the same because this U value or H value or even K, it is depend on temperature increment. 1 degree increment in the unit of Kelvin and 1 degree increment in the unit of Celsius is the same increment, okay? So if I have BTU per hour per feet square per Fahrenheit. So this is the unit of U value in the field case. This kind of question can be either true or false question. What if I change from Fahrenheit to Röntgen? Is there going to be anything change? Nothing, because U value, K value, it is depend on the temperature increment. The increment of 1 Fahrenheit is the same as 1 increment of 1 Röntgen, okay? The only time that we use the absolute value is when we use gas law, okay? PV equal to Z nRT, that has to be Röntgen. Or we also use the absolute pressure in compressor calculation. We use absolute temperature in compressor horsepower calculation, okay? Alright, so this is overall heat transfer coefficient account for heat transfer from oil to the inner wall, from the inner wall to the outer wall through conduction, and from the outer wall to the environment to another convection. If we have very good conduction, okay, very good conduction means thermal conductivity is very high. The material that have high thermal conductivity, for example, copper. Copper has thermal conductivity about 400 watt per meter per Kelvin. That is copper, okay? If you don't have copper, okay, copper has very high thermal conductivity. If you have very high thermal conductivity, let's say K pipe become infinity. What happened to this term? Arif, what happened to that term? Does it become infinity or zero? Kp go to infinity, then what happened? Zero. So this term becomes zero, right? If K sub P go to infinity, that term is gone. What if outside the wind blow very fast? We have very good heat transfer for the outside. H sub O become, what's your name? Scott. What is the value of H sub O? Let's say it's become infinity. What happened to this term? Become zero, okay? So if outside heat transfer is very fast, this term becomes zero. Okay. So this telling me that U value, okay, this U value, U times R is restricted by the lowest heat transfer process. Okay. If I have inside heat transfer very high, that is zero. Outside heat transfer very high, that is zero. This means U value is dependent upon just heat transfer across the pipe. Okay. This is a pipe without insulation. What about the pipe with 2 layers of insulation? So the pipe is a red color. The first insulation layer is the blue one. The second insulation layer is the gray one. Christian with a K. Alright, so what happens if all these terms go to zero? What happens to U value? Go up or go down? Go up. Go up.
Or down, sorry.
Down. Or down. Up or down. So case 1, okay, take a look one more time. 1 over U times R equal to 1 plus 1 plus 1 plus 1. Okay, Christian with a K. So if this thing becomes 0, 0, 0, what happens to U value? Go up or go down? Case A, okay, 1 over u times r equal to 4. Okay. Case B, that thing becomes 0. 1 over u times r equal to 1. A is more than B or B is more than A. I mean u value of case A is more or less. Christian. Okay, who do you want to help you?
Well, that's Marty.
Oh, Marty. Okay, Marty. U value in case A is about, okay, let's say R is 1, right? Okay, U value in case A will be about 0.25. Okay, U value in case B will be about 1. Do you agree with that? Yes. Okay, so U value in case A is 0.25. U value in case B is about 1. So B is greater than 1. Okay, could B is greater than 1. So this means when I delete that term, delete that term, delete that term, delete that term, and the right hand side value becomes lower, U value go up. Okay, does it make sense? Of course, it makes sense. If I have, okay, let's make simplification, okay, just for mathematical argument. Okay, 1 over u equal to 1 over h plus 1 over ho. 1 over ho. So if hi equal to 1, ho equal to 1, what happened to u value? 0.5, right? 0.5. So what is that telling me? U value won't be higher than any of each of that, correct? It is what do we call this kind of summation? Geometric or something? I have to Google it. No? Okay. What I know for sure is U value won't be, so in this case U value becomes 0.5 if each of these things is 1. Okay, so U value cannot be greater than any of these. So it is a net heat transfer coefficient account for every restriction. So if I have very good heat transfer over here, very good heat transfer over here, but bad heat transfer over here, the U value will be lowest of them all. Okay, lowest of them all. Make sense to you? Okay. This kind of average is the same thing that you do for the resistor, right? You add a resistor in parallel, in series. Is it in parallel when you add a resistor in parallel? You add a resistor in parallel, the net resistance becomes less or something. So this is same. So U value will be lowest of them all. Okay. This thing also implies that sometimes some term is not important. Okay? Sometimes is not important. For example, if I have insulation, let's say I use polyurethane has very low thermal conductivity. For example, 0.2, okay, watt per meter per Kelvin. So let's assume that that is thermal conductivity of the polyurethane that we use for the insulation layer. Okay. This is going to help us to do quick approximation. Okay. In the exam, if you want to do an approximation, hey, U value is very low compared to by thermal conductivity compared to the flow of everything. We may say at least 1 over u times r is that 0.2 over there and that the thickness. Okay, we may delete every other term, okay, and consider just the term that is the insulation layer for a quick estimation. Okay, for a quick estimation, the actual u value will be lower than the estimation that we have. Okay, so when I have insulation layer, I want you to do quick estimation. I say, okay, U value 1 over u times r at least equal to natural log of the thickness, I mean R3 over R2 divided by thermal conductivity of the insulation layer. So this means U value that I get is the maximum possible U value. Make sense? It is a maximum possible U value because when we add other heat transfer restriction, U value will go down, go down, go down. So if I do it like this, the U, I neglect all other terms, have just that term, the U value that I get will be maximum possible U value. When I use maximum possible U value, I plug it back into that equation. So U value means heat loss, right? If we have high U value, this means we have good heat loss. I mean, a lot of heat loss. If we have low U value, we don't have much heat loss. So when I plot this equation, I will get the temperature profile versus distance, okay, like this. It decays exponentially, okay. So if I use maximum possible U value, I will get lowest possible temperature estimation, okay. The actual temperature cannot be lower than that. So this is the conservative approximation. At most, we have just that much heat loss. You understand? So let me repeat myself one more time. I have several terms, but I neglect every term except the insulation layer. U value will be maximum U value. I put that maximum U value means maximum heat loss. So maximum heat loss, I will get lowest temperature profile. So that is lowest possible temperature profile along the pipe. If I consider other term, I will have less heat loss. So the temperature inside the pipe is actually will be warmer. Okay. The important thing with this lowest possible temperature profile is it is the worst case possible for the pressure drop calculation. When the temperature is low, viscosity is high, and when viscosity is high, is the maximum possible pressure loss. Okay? So if we have a simulator do a very good job, we can double check. If the simulator get any temperature lower than what we say, is wrong. Okay? Alright, this is a quick check for the result from any simulator. It worked for any pipe that have heat loss. Okay? It worked very well for liquid flow. Gas flow, it doesn't really work because we have Joule-Thomson cooling. Okay? When we have the pressure drop, we have Joule-Thomson cooling, but this doesn't account for any Joule-Thomson cooling. Alright, let's find out how do we do the calculation of this term. That is easy enough, right? We need to know radius number 2, okay, radius number 1, okay, radius number 2, radius number 1, do the ratio, put it in the natural log, divided by thermal conductivity. What is this? Thermal conductivity. Is it of the flow or of the material? Material. It's not of the flow. It's a material that is between R2 and R1, okay? H sub I over there is a heat transfer coefficient. It is not a fluid property. It is a flow property. If we flow fast, H value become higher. If we flow slow, H value become lower. Okay, that H value is a flow property. The way to calculate H value is come from correlation. The correlation is dependent upon whether the flow is laminar flow or turbulent flow. If we have turbulent flow inside the pipe, we have one correlation. If we have turbulent flow outside the pipe, we have another correlation. So most of the time when we actually doing it, our job is open the handbook. For example, Perry Engineering Handbook. Perry Handbook will tell this correlation is for internal flow or external flow. Is it flow inside a circular duct or square duct or something like that, okay? In this lecture, I present you H value calculation. This is from the correlation. Number 1, the Tasco error. Number 2, Galilinski. Do you write this in the exam? Not really. You write just that. Okay. The rest, if you have to use it, I will provide it because you don't have enough time to calculate it anyway. All right. These two equations is for H value, heat transfer, convective heat transfer coefficient for flow inside the pipe. Okay. Reynolds number is Reynolds number of the flow. Prandtl number is of the fluid. Prandtl number is mu Cp over K. Okay, the formula is given over here. Mu multiplied by Cp is a P over K. Prandtl number is a comparison between viscosity, okay, and thermal conductivity of precisely nu over alpha. Okay, this I understand that this is a new concept, okay, but not quite a new concept for mechanical engineering or something. So alpha is thermal diffusivity. Okay, alpha, the name of alpha is thermal diffusivity. The name of nu is momentum diffusivity. Both of them has the unit of meter square per second. So it tells how fast that momentum will propagate or how fast that the heat will propagate. Okay, so Prandtl number tells whether heat transfer better than momentum or not. Okay. In what kind of fluid? So by the way, this is fluid property. Prandtl number is not a flow property, it's a fluid property. Okay. For some fluid, Prandtl number is very small. I mean less than 1. What do you think that fluid could be? Trouble? What is a fluid that Prandtl number is lower than 1? That can transfer heat very quick, but transfer momentum not quick. Oh, okay, you're not teacher. Jesse, what do you think? You have seen it before. It is downstairs in the lab that is closed, and you don't have access to that lab. Okay? If you see that fluid, you should not touch. It's shiny. Mercury, okay? Mercury flow, but it can transfer like heat very good, okay? Or if I have molten metal that flow, okay, it transfers heat very good, okay? Typically for oil, normal oil, I mean crude oil, Prandtl number will be 10, 50. Crude oil maybe 200. So most of the oil that we're dealing with, it doesn't really transfer heat. Okay, it transfers heat very slow. So it transfer momentum a lot better. So mu for our case is like 50 and above. Sometimes it's 10,000. Okay, if it's very viscous. Sometimes it's maybe 1,000 or 50. Let's talk about typical value. Okay, I know that every crude oil has its own specific value for the fluid property, but typical value, typically, you should know this. This is not in the exam, but you should know it anyway. Thermal heat transfer, thermal conductivity of crude oil is about 0.13 watts per meter per second. Okay. Cp of oil is about 2,000 Joule per kilogram per Kelvin. Okay, Joule per kg per Kelvin. Mu is about, how much is the mu of oil? For crude oil, okay, specific gravity, like maybe API gravity of 10 to 30, mu will be, can vary from 2-3 centipoint if it is condensate, or it's dependent on temperature, right? So this can be 10 to 20, 50 or something, okay? So my point is, mu is 2 digit, like 10 centipoint. 10 centipoint is 0.01 Pascal second, okay? You have to be able to convert from different unit. Alright, Prandtl number is fluid property. Basically, you get it from the handbook, okay? Or Google it. Plug it in, put the Reynolds number in, then we can calculate Nusselt number. Nusselt number, the physical meaning of Nusselt number is the comparison between heat convection over heat conduction. Okay. If Nusselt number is more than 1, this means we tend to have convection better than conduction. For laminar flow, Nusselt number is about 3 or sometimes it's 4, okay? Far away from the inlet. You will notice that Nusselt number is dependent on that value. This is the diameter of the pipe, D is the diameter of the pipe, Z is the distance from the inlet. At the inlet, Z value is 0, okay? Z value is 0. 1 over something over 0 is infinity. This makes Nusselt number become infinity. Is that a typo? No, it's not. It is that. Okay. At the inlet is infinity. So H value at the inlet is infinity. Can we do anything? No, we cannot do anything. What do we do then? So this equation gives me the Nusselt number at the point value. Okay, it gives me at the point value. But what we really need is the average Nusselt number over a certain interval. Okay, over a certain interval, I mean from 0 to 10. Okay, we do the integration. For pipeline calculation purpose, we drop this term. Okay, we drop that term, and you will become happier because it becomes constant, right? Okay. So Nusselt number become 1 value. But just so you know, not in the exam, but you should know that near the inlet, Nusselt number is higher than away from the inlet. Okay. So in the exam, when I give you this formula, I say fully developed heat transfer, you may assume neglect those terms. Okay. But I don't think exam is going to be that difficult. Alright. So Nusselt number change with position if we are far away from the inlet. For example, 35 diameter away from the inlet, we should be safe by using just this term. Okay. Once we have Nusselt number, we know thermal conductivity that is of the flowing fluid. Okay. And inner pipe diameter, then we can get H value, and that is going to be H sub I, which is that term. So you can see that it is quite troublesome to get heat transfer coefficient of flow inside the pipe, right? The correlation is long, we have to put the value in, okay? But now, it's just a correlation, okay? We have correlation, put the value in, we get the H value, okay? Any question on this? H sub I. H sub O, outside heat transfer coefficient, is the same. It's from another correlation, but this time it's a correlation for external flow. For the external flow, okay, we skip that boundary layer theory, everything, okay. For the external flow, we have same formula. Nusselt number of outside is heat transfer coefficient of environment multiplied by D sub O, outer pipe diameter, or the most outer layer diameter, divided by thermal conductivity of what? Of the fluid that is flowing outside. If we have the pipe in the air, so that K will be thermal conductivity of air, not thermal conductivity of the pipe. Nusselt number, okay, this thing is relevant. Nusselt number is flow property. Therefore, the value of K is of the fluid that is flowing. Okay. In the exam, we may say Nusselt number equal to H D over K, and that K is the thermal conductivity of the pipe. True or false? You say false. All right. So the formula is the same. I mean, this formula is the same. The empirical correlation to estimate H sub O. H sub O is that term. External heat transfer coefficient is from C value multiplied by Reynolds number to the power of M, Prandtl number equal to 1/3. So basically it's another correlation based on Reynolds number of the outside flow. And the value of M and C value It depends on how much is the Reynolds number. Okay. This is good for both subsea and air. Okay. So basically, it's a correlation. Once we substitute the value in the correlation, we get H sub O, outside heat transfer coefficient, except it is a little bit lengthy. Okay. In the exam, you don't write that, but if you need to use, I will give it for you. Okay, I will give that for you. What you need to know, okay, I will give that to you and give the table to you. Or I may not ask about it at all. Okay, I have several options. Prandtl number is Prandtl number of the fluid that is flowing. If we have subsea pipeline, the fluid that is flowing around the pipe is water. So that is Prandtl number of water. If we are pipe in the air, that fluid is of the air. Okay. Reynolds number of O is rho UD, rho BD over mu, but fluid property is a property of the fluid that is flowing that causes heat loss. Okay, velocity is the average velocity and the characteristic length is the outer diameter. Any question for me? It is just using a correlation, right? Okay. After we know outside fluid property, inside fluid property, we know outside Reynolds number, outside Prandtl number, we know inside Reynolds number and Prandtl number. We plug the value in, we calculate Nusselt number. After we get Nusselt number, we can calculate H value. Okay, we know heat transfer coefficient. We substitute those heat transfer coefficient back into here. Okay, we go all through this pen just to get that H value. Okay. And then if we know the thermal conductivity of each insulation layer, so the blue layer has that K, another layer has another K, and the pipe thermal conductivity, we know the thickness, okay, of each layer. We know R2, R1, we put everything in, then we get the U value. Once we get the U value, we substitute it back. Okay, by the way, when we do the calculation, we don't really want to get only the U value. There's no point to just get the U value. Typically, we just get U times R. Okay, those U times R over there equal to this whole thing. Okay, typically we get U times R, and we substitute the U times R right there. So UD equal to 2 multiplied by U times R. So if it's U that is reference to the inner pipe wall, that is R is reference to the inner pipe wall. So U multiplied by D over there equal to 2 multiplied by U and R in that equation. Alright. The next trick that sometimes people fail is calculate outer pipe diameter. Okay. I have pipe diameter of 5 inch. Okay, 5 inch. And I have insulation layer thickness of 1 inch. Okay, that is DI. So in this case, so this is, that is outer diameter. 5 inch is outer diameter of the pipe. Okay, 5 inch is outer diameter of the pipe. Let's say the pipe is that blue thing. So outer diameter of the pipe is 5 inch. If I have delta of 1 inch or insulation layer of thickness of 1 inch, the total outer diameter, which is a characteristic length to calculate outside Reynolds number, must be delta multiplied by 2. Okay, so DOO, which is super outside, everything included, equal to 5 plus 2 multiplied by thickness. Don't forget that 2. Okay, the reason that we have that 2 is because when we say thickness is just that. So that length is 1 inch, right? But that thickness also apply on another side. So don't forget to multiply by 2. Okay. That's it. Substitute it back into the main equation, then you get temperature profile everywhere. Good. What if the pipe is buried? How the engineer will do the calculation? If the pipe is buried, we need to know the depth, thermal conductivity of the soil, And there's a formula to calculate the net heat transfer coefficient. For example, heat loss, okay, in the soil is dependent on if it is fully buried or partially buried. Okay, we need to know the K value of the soil. Okay, this is the calculation of this buried pipe is not in the exam. Okay, even if your calculator cannot do hyperbolic cosine, you're fine. So if the pipe is buried, okay, it depends on how much it will be partially buried or completely buried. There's a way to convert from the depth that is under the ground and the thermal conductivity of the soil to edge soil. Okay. So at the end, we will have one more term pop up over here, which is a heat resistance due to the soil, okay, because the pipe is buried. This is maybe too more complicated. It's just too much, okay. But just so you know, even if the pipe is buried, there's a way to calculate heat loss, okay. We skip all these equations. People even go to the point where they measure soil thermal conductivity. In the Gulf of Mexico, we need to know soil thermal conductivity, and the soil thermal conductivity is dependent on how much water is in that soil. Okay, it's going to that depth because they want to know. Even just forget about buried pipe, just use insulation layer. Is that okay, or we have to insulate? And how much is the benefit of burying the pipe? They need to do the calculation to tell it, okay? And I just tell you, there is a way to do it, okay? We don't tell you on that, and that's a formula. Calculation example, this thing is show you for the case of constant fluid property. Basically, we get everything, okay? And eventually, look at this, we get H sub O, okay? And we have H sub I, and we have H times R, and we calculate U value. So the calculation step is number one, know fluid property, know the flow property. Number two, calculate Reynolds number inside, Prandtl number inside, Reynolds number outside, Prandtl number outside. Then plug the value in either Lucas-Boelter or Genelinsky for the case of turbulent flow to get inside Nusselt number. Okay. This is just to get inside Nusselt number for the case of far away from the inlet. It may seem to you like it has a lot of details, but basically it's very easy. Get Reynolds number, plug that Reynolds number into Nusselt number equation, get H value. You may see the reason why I don't test you on this, right? Because it's quite long, okay? But the grad student can do it. What you need to know is, what is the calculation step, okay? So step one, use those correlations for flow inside and flow outside to get H value. So once we get H value, we calculate U value, okay? U value. And if you notice something, this is a pipe that is not insulated, okay? The first term is 0.1. Second term is 0.003, third term is 0.67, okay? If we insulate the pipe, we may have some term that is equal to 5, okay? So if we may be able to neglect everything except the insulation layer, okay? To do the approximation on the maximum heat loss. Okay, just calculation step. After we get HO, HI, calculate the U value, plug it back in to calculate the exponent, okay? Exponent, and then put it in the first equation. This is the exponent value. Put it in the first equation, we get the temperature equation or temperature profile. And then we can plot it. This is an example for the buried pipe, just for your reference. Okay, we don't test you on that, but just for you to know that it can be done. Okay, it can be done. This is a calculation result. Bad pipe, but we buried it above the ground with insulation, buried with insulation. So this is temperature drop with distance. Okay, So it can be done. Alright. Maybe okay. The buried pipe. You may notice something. You see this 0.78 and 6.8. The term that comes from the buried pipe is 6.8. The term that is from something else is very small. So this means even if we neglect those things, the value that we get is not going to be that far off. It will be the worst case scenario. Agree? Okay, you agree? You sleepy? Okay, so it will be the worst case scenario. Why do I have to mention this again and again? Because the step to calculate HI and HO is very painful. Okay, it's very painful. You see the formula, right? Genelinsky equation, external flow. Those steps is painful. We may just take that. Okay, or the case where we insulate the pipe and bury it, you will see that, okay, sometimes the insulation layer, that is the only thing that matters. Okay? Alright, this is how do we account for the change of fluid temperature, fluid property. We don't go over that, but it can be done. Okay, the last slide. I hope you have this in your not Dakota project or something. Try to add it in, okay? Regardless of whatever calculation you made, this is a good guideline for you to follow. The guideline is, okay, if we are over here, okay, let's say we are over here. We buried 5 inches. Is that good? It's good for the case of not getting freeze. Okay, but it's not good for the farmer. When they grow cotton, they will break the pipe. You have to bury it deeper than that to prevent them break the pipe. Okay, 3 feet. I think 42 inches is good enough. Okay, so in Texas, the worry is not about it getting frozen. The worry may be about the cotton field may damage it. So on short Texas gas pipeline buried at the depth of 42 to 48 inch, okay. Alaska pipeline is not even buried, but put above the ground, okay. Alaska is quite cold, but they do the calculation and they say, okay, let's not bury it, just put it outside, above the ground. Pipe roughness, air property, or thermal conductivity that used in this calculation is from those websites. This is a reference. Okay, let's go through. Any question on this? The question for me will be just, if I tell you the U value already, and I tell you that U value is referenced with the inner pipe diameter, and I give you the inner pipe diameter, I give you mass flow rate of oil, which is that thing, I give you thermal conductivity of oil, specific heat capacity of oil, I tell you the inlet temperature, environment temperature, and I tell you, hey, at 2.5 miles away from the inlet, what is the expected temperature at that point? Based on constant fluid property assumption. Can you do it? You should, okay? The only trick is, you need to know that, okay, 1 mile equal to 5,280 feet, and 1 foot equal to 0.3048 meter. We convert everything into meter and we substitute as a Z value. Because most of the time, those things is given in SI unit, okay? What about the temperature?